Welcome back. Today we're going to continue on with the 2018 free response question. We're going to start off with number 4. Now, number 4, they give us a table. Anytime they give me a table, I'm always thinking Riemann sums. All right, so the height of a tree they've given us is given by a twice differentiable function where h is measured meters and t is measured years. And then they've given us values for h of t for the table. Whoops, sorry about that. Let me go ahead back here. Put that in pen mode. There we go. All right. So the first question says, use the data in the table to estimate h prime of 6. Now, they're using us to estimate because remember h prime, that is, of course, a derivative. And we can't find the exact derivative because we're not given a function. So we're going to use h prime of 6 as an approximation. Now, you might remember, if this is an approximation, this is going to be our average rate of change for a rock right there. And to get that, it's an approximation, so we're using squigglies. I look where 6 is located. Well, 6 is between 5 and 7. So I can say that h prime of 6 is approximately the slope. Remember, derivative means slope for us. So how do you find slope? Well, that's just you changing your y's over your change in x's. So it's going to be h of 7 minus h of 5 over 7 minus 5. Please include the steps. The AP really loves to see it. Now, since I'm looking for the approximate slope, I can use my equal sign instead of my squiggly now. And this is going to become 11 minus 6 over 2, which is 5 halves. Now, you get 1 point for that. But now they ask us to interpret the meaning of h prime of 6. What does that mean? Well, this means at t equals 6, at time t equals 6, the height of the tree you should put years too. At 6 years, at t equals 6 years, the height of the tree it's positive, increasing at a rate of 5 halves. What's going to be the units? Oh yeah, meters per year. Plus 1 for that. Pretty easy to do. All right, so let's go to question B. Don't miss question 1 there. Question B. It says sorry. B was down here, sorry. Roll down. There it is. Explain why there must be at least one time t between 2 and 10 years such that the rate of change is 2. Now, there is no function for this to show that. So what they're looking for is the time between 2 and 10 years that is changing at 2 meters per year. For me, this sounds like MBT. So I want to pick a time between 2 and 10 years. Now, 2 and 10 don't work in this case, so we got to get creative. So let's see. Look at the difference here. Between 3 and 5, that's 2 years right here. And the height changes by 4. Well, that's 4 divided by 2, which is 2. So we're going to pick the 3 and the 5. So we can say that h of 5 minus h of 3 over 5 minus 3. Remember, h of 5 was 6 minus 2 over 2 is 2. And that's what we want. Now remember, this is my average rate of change right there. So this is MBT, so I'm going to set it up. Remember, first of all, for MBT, you have to be continuous. So we can say h of t is continuous. You can read that on the domain. Hard bracket for the domain, 3 to 5. And that's a 3. Differentiable, and the derivative will use this on the open bracket, 3 to 5. And because we just said that the average rate of change is 2, therefore, somewhere, we talked about this earlier, on the domain 3 to 5, the open bracket 3 to 5, h prime of t has to equal 2 by the mean value theorem. And that's it. You get plus 1 for getting the range, plus 1 for your answer. If you don't mention MBT, you're going to lose that point. So make sure you have the word MBT there, okay? All right, let's take a look at part C. All right, part C, there it is, our trapezoidal sum. It's like our Riemann, but it's a trap. It's a trap, right? Okay, So with 4 subintervals indicated by the data to approximate the average height. Oh no, what's average height? For the time interval between 2 and 10 years. So this is our phase. Well, what is our average rate of average height? B minus A from A to B, f of x dx. For us, it's going to be 1 over minus 2 from 2 to 10 h of t dt. So it's going to use it. So I'm going to set my trapezoids. Now, dude, draw your trapezoids, draw your rectangles. The AP likes to see where you got your work from. And the time intervals were 3, 5, and 7. Not drawn the scale, of course. The height at 2, we were told, is 1.5. At 3, the height was 2. At 5, the height was 6. At 7 years, the height of the tree was 11 meters. And after 10 years, the height of the tree was 15 meters. And there's our trapezoids. Again, the AP likes to see this. So this is going to be approximately. Now, don't forget about this value right here, the 1/8. And I'm just going to show my work. The first one, 1/2. You could just add them together. That's 3.5 times 1 plus 1/2. The next one's going to be 8. 6 plus 2 is 8. And the difference there is 2 plus 1/2. 6 and 7, 11 is 17. It has a base of 2 right there as well. And then the last one, 1/2. 11 and 15 is 26. And the width down here is 3. And there we have it. Now you're going to get 1 point for just showing your trapezoids. And then you get 1. Now make sure you include your units, the average height. So let's go and get the height here. This is in meters. Time is in years. But this is 1 over years. Those cancel. So we're left with meters. So this is units in meters. And you get 1 big gigantic point for the final answer, including that 1/8 right there. So that's pretty quick and easy to do. Do not simplify. If you do simplify, you would get 263 over 32 meters. But you don't have to do that. All right, part D. We're mathematicians. We love the part D. All right, it says the height of a tree can also be modeled by this function. So now they've given us g of x, which models the height of a tree as an equation, where x is the diameter of the base of the tree. When the tree is 50 meters tall, so they're giving me the height, so they're giving me g right here. The diameter of the base of the tree increases at a rate of 0.03 meters per year. According to this model, what is the rate of change of the tree with respect to time in meters per year at the time when the tree is 50 meters tall? All right, so, oh no, you know what this sounds like to me? Sounds like a related rate. So let's see what we're looking to find here. According to this model, we are given, let's see what we're given. Let's go and write out what we're given. We are given g of x is 50. G is 50. Now, if g is 50, what does x have to be? Well, if g is 50, then x has to be 1. You can just plug it in and solve for that. And we are given that the diameter of the tree is 0.03. So remember, x is my diameter, so they're telling us dx dt is 0.03. And then what that's to find here, at what rate is the height of the tree changing? So we're asked to find dg dt. So let's go and take a look here. Well, we know g of x is equal to 100x over 1 plus x. Quotient rule, dg dt would become low 1 plus x d high 100 minus high 100x d low, which is just 1. Don't forget the derivative of low, 1 dx dt all over the bottom square right here. Remember, this right here is your chain rule. And just for taking that derivative, they give you 2 points. And now we're going to plug in everything. So dg dt equals, we can plug the 1 in, so this becomes 2 times 100 minus, again, remember x is 1, minus 100 dx dt 0.03 over 2 squared, which is just 4. So we can go 1 plus 1 squared. And it is okay to leave it like this if you like. Oops, sorry. Oh, no, the dxdt, sorry. I did mess up a little bit. Oh, no, the dxdt is on the side there. So times 0.03. There we go. It's all of this times the dxdt. And the reason for that is because this had a dxdt on it as well. So we can just factor out that dxdt there. So, anyway, so when we simplify all of this, now one, you can just leave it like this if you want to, and this is going to be meters per year right there, and that is 1 point as well. All right. Anyway, so I did mess up there. So let me go over this chain rule again. When we did low 100 plus x, d high, this became 100. There was a dx dt there, and there's also dx dt here. We can just factor that out. You don't have to if you don't want to. So this should have been times by 0.03 times 0.03 as well. All right, so take a look at this one again. We'll go over this one in class, okay? And I'll see you guys then. And go on to go to question number 4, and we'll continue on with the 2018.